So today we're going to start our second portion of the class, and that is spectroscopy. So the first part of the semester we were focused on knowing different forms of purification. Now what we're going to do is we're going to focus a little bit more on the way to determine the structure of an unknown molecule using different spectroscopic methods. And the first method we're going to discuss is NMR, nuclear magnetic resonance. So there are two different types of NMR. One of them is called proton NMR. The other is called the other is called carbon-13 NMR. And both of these tell us some useful information. One of the proton NMR tells us the number of hydrogens and the different types of hydrogens in a molecule. And carbon-13 NMR tells us the number of carbons and the different types of carbons in a molecule. For the purposes of the lab, we're going to be focusing on proton NMR. It's a little bit more complex than carbon NMR. If you can do proton, then you can do carbon. Carbons, you count the number of peaks, that's how many carbons there are. But proton tends to be a little bit more complicated, so we're going to focus there. Now, so I want you to be very primarily focused on being able to interpret a spectra. So this is the spectra that you're going to be responsible for interpreting. So notice the different axes here. So let me get my pencil here. That's not it. There we go. So let's see. So notice that there's different types of spectra. So here we have, on this axis, we have intensity. And then on this axis, we have chemical shift. Now, chemical shift is simply telling us where the signal is showing up. So these are the individual signals. Now, so for example, this one shows up around 3.2. This one shows up around 1.2. So that's telling us where does the signal show up. Intensity is just telling us how strong that signal is. There is some terminology that you need to be familiar with, the term upfield and downfield. So this spectrum actually goes from close to 0 to close to 14. So you can't really see it over here, but it actually goes to 14 over here. So the closer you are to 0, the more we say you are upfield. So we need to be familiar with that language. The more you're closer to 14, the more we say you are downfield. So, so just some terminology here. Now, this peak here that's at 0, this is called the TMS reference peak. This is not actually part of your molecule, so if you see it there, it's just there to tell where 0 is. Now, what's TMS? TMS is tetramethylsilane, so it looks like this. So this is tetramethylsilane, TMS. So if you see that, that peak there, keep in mind that it's not part of your molecule. It's just telling you where 0 is. So you might want to keep that in mind. All right. So this is what you're going to be responsible for interpreting. We're going to go through a lot more in depth about what these signals mean, but we just need to orient ourselves with what the values are that we're looking at here. All right. So um, the next thing that we're going to, oops, let's go back. All right, so the next thing that we're going to discuss here are the different features of an NMR spectrum, and that is going to be the number of signals, the position, where do they show up, the intensity, how strong are those signals, and then spin splitting, what do those signals look like? So those are the four concepts that we're going to talk about today. And let's start with the first two. Let's start with the number of signals. So when we look at the number of signals here, the way you can determine whether a molecule is going to have the same or different number of signals is if they're in the same chemical environment. If we look at the different hydrogens and they're in the same chemical environment, they're going to produce the same signal. And we're only looking at the hydrogen environment because this is proton NMR. So if they're in the same chemical environment, they produce the same signal. If they are in different chemical environments, they are going to produce different signals. So for example, if we look at this molecule right here, right, this is methane. How many different protons do you think you would see here? Think about that. How many protons, different protons would you see? Yeah, hopefully you look at this, you're like, well, they're kind of all the same. They're all in the same chemical environment. You're absolutely right. All of those protons, they're in the exact chemical environment. So what you'll see here is that we would only have one signal. And we see that signal here. I'm going to change colors. We would see that signal right here, right? There's only one signal because they're all the same. All right, let's try this one here. All right, let's try this one. How many signals would you expect to see in this molecule? All right, all right, hopefully some of you think that you would see just one signal, right? There'd be one signal. All of these hydrogens, again, are in the same chemical environment. If that confuses you, try this. Look, some of you may have thought that there were two signals. You probably thought, okay, well, these hydrogens right here are on carbon, on one carbon, and these other hydrogens right here are on another. That's probably what you thought. But that's not how we determine number of signals. Remember, if they're in the same chemical environment, they produce the same signal. So one way to look at it is these hydrogens right here are on a carbon, right? They're on this carbon that's next to a CH3, right? So those hydrogens are on a carbon that's next to a CH3. All right, now let's look at the other hydrogens. These hydrogens here are on a carbon that is next to a CH3, right? So they're actually in the exact same chemical environment, okay? So if that's the case, then they're going to produce the same signal. If that still doesn't clear things up for you, try it this way. If you thought that those two hydrogens were different, then take one of those hydrogens. So let's say that we have this molecule right here, and take one of them and replace it with fluorine. So here we go. Here's my fluorine. All right, just take one and replace it with fluorine and name the molecule. If I were to name this molecule, this would be 1-fluoroethane. Right? Okay, now take the other one and replace it with fluorine. So I'm going to put these hydrogens back here and replace this one with fluorine. If I do that, this is 1-fluoroethane. So the name is the same, right? So if the name is the same, then those signals would be the same. So again, we only see one signal here, right? Only one signal there. All right. All right, so let's see. Let's try this one. How many signals would we expect to see here? All right, hopefully we see that there will actually be two signals here, right? Because in this case, we see a signal that is on oxygen. So we see this signal right here. And then we see these signals right here that are on carbon. So we see those and we see that one there. So we would see two signals, and that's exactly what we see there, right? Two different signals, one of them pertaining to the blue hydrogens, the other pertaining to the red hydrogen. Okay, so again, if they're in different chemical environments, they produce different signals. So let's do some more practice here. I'm going to draw some, and then you guys, you guys pause the video, and let's see how well you do here. Okay, so I'm going to draw some. You guys pause the video and see how well you do. And there'll be a question that comes up to ask you how many signals each one does. So let's start with this one here. Go ahead. How many proton signals would you expect to see in this molecule? And you'll see the question pop up so that you can answer. All right, so hopefully we looked at this and we see that there are going to be two signals here, right? There are going to be two signals here. If that confuses you, let's take a look here, all right? So here's one hydrogen environment, right? So if we look at them all, and then here's another environment, and I'm going to go ahead and switch colors here so we can see the second environment. Let's go ahead and use black. Here's the other, right? So those are the two signals right there. So just so that we can clear this up, let's say, okay, let's look at these orange hydrogens over here on the far left. These hydrogens are on a carbon next to a CH2, next to a CH3, right? Those hydrogens are on a carbon next to CH2, CH3. All right, now let's look at these black ones. These hydrogens are on a carbon with a CH3 this way and a CH3 that way. So can we agree that those would be different? Yeah, they're in different chemical environments. But now let's look at these other orange hydrogens over here. These hydrogens are on a carbon next to a CH2, CH3. So what we would see is that, again, those hydrogens would be the same, right? Because they're in the same chemical environment. Now, we can also do this. We can cut this molecule right in half, and we also see that this molecule is symmetrical, right? So those on the end there would be in the same chemical environment because this molecule is symmetrical. All right, let's try another one here. Let me switch my colors. All right, go ahead. Let's determine how many signals. All right, so hopefully we determined that the number of signals here in this case is going to be 3 signals, right? It's going to be 3 signals here. So if we look at this, right, there's this hydrogen environment right here. Then there's this one right here. And then this one here. Oh, that was a lot thicker. There we go. Nope. So I'm not sure why it's showing up that way, but you see, you get my, hopefully understand what I'm talking about here. So in this case, we have 3 signals, right? If we look at the orange hydrogens, those are directly next to, on a carbon next to an oxygen, compared to the pink hydrogens, those are on a carbon next to a carbon, so different chemical environments there. And then these two hydrogens here that are on this carbon, those has an oxygen to one side and a CH3 to the other. It's a completely different chemical environment. All right, let's try another here. And hopefully my pencil will work. Oh, because that's a highlighter. Now I understand. See, you guys, y'all get to see me learning stuff. All right, so let's try this here. Right. Uh, yeah, let's give that one a shot here. All right, so hopefully you realize that there are actually another 3 signals here, right? 3 signals here. Um, so if we look at it, here's one hydrogen environment. Here's another. And then here's our last one. Right, so 3 different hydrogen environments there, right? This CH3 is next to a CH2. This other green CH3 is next to a carbonyl, so different chemical environments there. All right, let's do one more, and let's see how well we do here. Let's do that one. How many signals would you expect to see here? All right, so hopefully we realize that there is only one signal here, right? One signal here. And if we look at that, right, we can draw out all those hydrogens. All of these hydrogens here are going to be in the exact same chemical environment. They're all going to be next to a CH2 on both sides. So there's only one signal here. All right, so this is something that you're going to want to practice, right? And this lab that we're doing this week, there's no real experiment that's being done. There's a worksheet that's going to have more practice problems on there. But keep in mind that that worksheet's not going to be enough for you to master this. So please make sure that you're doing plenty of practice in your textbook. This would be in the newest version. There's a complete section for NMR spectroscopy. I think it's part A, and you can find that in the table of contents of your Janice Smith textbook. All right, so this is how to determine number of signals. The next thing that we're going to talk about here is how to determine the position of signal. Where is the signal going to show up on the NMR spectra? So again, I want you to appreciate the theory, but I'm primarily focused with you being able to interpret a spectra here. Now, with that said, when we think about nuclear magnetic resonance, right, we have this spinning nucleus here, and it's protected by an electron cloud, right? So nucleus means that a spinning nucleus, magnetic means we're going to put this into a magnetic field, into a machine that stimulates a magnetic field. And when we do that, that magnetic field is going to try to hit the nucleus. Well, the more electrons that you have around, so the larger this electron density, the more protection you're going to have from that magnetic field, right? So you can imagine that the magnetic field tries to hit it, but it hits the electron cloud, and so it's protected. So at that point, we say the nucleus is shielded, right? It's shielded. It's protected. Now, if the molecule is shielded, so remember that we have a spectrum, right? A spectrum here that goes from 0 to 14. Well, if it's shielded, that means that it's not going to feel a lot of the magnetic field. It's going to be closer to 0, and this is what we say is shielded, right? We also said that this is uh, it's a term shielded, right? Um, Now, if it's closer to 14, right, means it is going to feel a lot of the magnetic field, that it's going to be getting hit pretty hard from the magnetic field, and we say that this is de-shielded. Okay, we say that this is de-shielded. So just keep that in mind when we're thinking about this terminology. Some more terminology here. The closer you are to 14, the more de-shielded you are. The closer you are to 0, the more shielded you are. All right. Now, and that's what we can see here, right? So imagine we have a methane group right here, but if we take one of those hydrogens and we replace it with a chlorine, right? If we replace it with chlorine, then what we see here, so that's what we did, replace it with chlorine, we notice that it starts to be more de-shielded, right? It starts to go more downfield, closer to 14. So we want to kind of keep those aspects in mind there. Okay. Now, um, so let's take a look at these two molecules here, right? So first things first, how many signals would you expect to see in this molecule right here? How many signals would you expect to see? Yeah, hopefully you say that you would see one signal, right? You see one signal, those molecules are the same, all right? Or those protons are in the same chemical environment. How many signals would you expect to see in this molecule right here? All right, hopefully you say also that there's going to be one signal, right? Again, we can cut this in half, right? And they'd be equal on both sides. Therefore, they're in the same chemical environment. So when we actually look at the spectra, both of them have one signal, right? We see that here. They both have one signal, but one of them is showing up close to about 0.9 right here, and the other is showing up around 3.2. So why do you think that's the case? Why do you think that this one signal is showing up around 3.2 and this one's showing up for 0.9? Why do you think that's the case? Yeah, it's going to be because of this oxygen, right? It's going to be because of that oxygen. Why? What's that oxygen doing? Well, remember, we said that electron density surrounds a nucleus here, right? And if the electron density is protecting the nucleus from the magnetic field, well, what happens when you put an electronegative atom, such as oxygen, right next to this carbon? What's going to happen? Well, it's pulling the electron density away, and I'll do a different color here, right? It's pulling the electron density away from the carbon, right? There's a dipole here pulling the electron density away. So as it's pulling it away, it's taking away its shield, right? So as it takes away its shield, then we're going to force it to be more de-shielded, right? We're going to force it to be more de-shielded. So that's why it goes a little bit more downfield. Okay, so keep that in mind. If you're close to an electronegative atom, the value is going to be a lot more de-shielded. It's going to be closer to 14, right, compared to 0. All right, so let's take a look at this one here, right? So how many signals would you expect to see in this case? So hopefully we look at this and we realize that there's going to be two signals here, right? We're going to see two signals here, right? Two signals, we see that here. We see this blue hydrogens and we see this red hydrogens over here. Now, the question is which hydrogen is going to be, there's one right here at approximately 3.7 and another one here around 2.2. Which hydrogen here is going to be at the 3.7 mark? Do you think it's going to be blue or do you think it's going to be red? Go ahead and click in. Which hydrogen is going to be at the 3.7 mark? Blue or red? Yeah, hopefully we realize that the one that's going to be at the 3.7 mark is going to be the red hydrogen, right? Because these here are much closer to the oxygen, which is a much more electronegative atom. So they're going to have a much stronger de-shielding effect. So we see those more at 3.7. All right. So let's think about this one here. Let's say we have this here. So between this, we should see two hydrogens here. And let's let me label these so we know two sets of signals here. So let's use here. So these would be HA, these would be HB. So which of these signals do you think would be more downfield? Which one would you be more downfield, more de-shielded? Yeah, hopefully you say it is going to be the A's, right? It's going to be the A's here. So the A's are going to be a lot more um, de-shielded because they're closer to this fluorine over here. And this fluorine is going to pull that electron density away, taking away its shield, right? So the number will be closer to 14. All right, let's try another one here. Let's try this one. So let's say now we have a fluorine here and a chlorine. So if we look at these different hydrogens, we still have two signals here. So HA and HB. The question is which ones would be more downfield? Which ones would be more downfield? Hopefully you realize, yes, that the ones that are going to be a little bit more downfield are going to be HB, right? Because fluorine is a lot more electronegative than chlorine, right? So it's going to be a lot more de-shielding effect. So these will be more downfield, right? So again, so we've talked about how to determine the number of signals, and now we've kind of given you an overview on how to think about where you would expect those positions, those signals to show up. Now, there are a number of different chemical positions that if you're probably in the lecture, you probably have to commit to memory. So for example, you'll know that the hydrogen on an aldehyde, they show up around 9 to 10. A hydrogen on a carboxylic acid shows up around 10 to 12, and so forth. In my lab, when we go onto Blackboard, you'll find a handout that gives you chemical positions that are even more specific, right? So you can use that rather than trying to commit them to memory. You are allowed to use that handout on an exam, and you should start getting used to using those. And you'll see another Panapto video that kind of walks you through where to find those handouts and how to use those worksheets. Okay, but you should be at least try to commit these to memory for your classes because in Organic 1 and Organic 2, you do not get handouts for the lecture courses, even though I am giving it for you to the lab. And for the MCAT, DAT, and PCAT, you're not going to have these handouts for either. So you might as well just commit them all to these here on this table to memory. All right, so we talked about the number of signals and we've talked about the position of signals. The next thing we're going to talk about is the intensity of signals. How strong is that signal? And then we'll talk about spin splitting. What do those signals look like? So when we're talking about intensity of a signal, if we look at this molecule here, there's two peaks, right? We can see that there are two different types of hydrogens here. So if we indicate them here, these hydrogens would be one chemical environment, and then these hydrogens here would be a different chemical environment. So two different sets of hydrogens, so we see two different signals here. Now, with that said, we're on the next category, which is intensity, or we also refer that to as integration. So we see the two signals here, but the truth is that if we were to zoom in on these peaks, so here's a zoom in, if we were to zoom in on these peaks, there's actually some area under this peak here, okay? So if we were to zoom in here, there is some area under this peak. Now, what integration is doing is it's measuring the area under the peak. So if we say that this is 3 units here, if we measure the area under the peak and it's 3 units here, and we say it's also 3 units here, then what we're saying is that the ratio of the area under the peak is 1 to 1. So that's suggesting that they're worth the same amount of hydrogens, right? So if signal 1 is worth 5 hydrogens, then that must mean that the signal 2 must also be worth 5 hydrogens. Now, but you want to keep in mind that this is a ratio. It doesn't necessarily indicate that this is how many hydrogens there are. Now, to make it simple for this class, the integration that I give you will be the number of hydrogens, just to make that very simple for you. But keep in mind that it doesn't have to be. If you were to actually take it on the instrument and you got the numbers off the instrument, they could suggest a ratio. But for simplicity in my class, the numbers that I give you will be the number of hydrogens that that molecule has. So if we look at this again, so two signals here, and we see that they're both worth 3 hydrogens, so the ratio is 1 to 1, right? But again, for the purposes of my class, instead of showing you, oh, it's 1 to 1, I will tell you this signal is worth 3 hydrogens and that signal is worth 3 hydrogens, just to keep it simple, okay? But ultimately, integration is one of the easier ones to think about here, because ultimately, if you can count, you can do integration, right? It's just counting how many hydrogens is that signal worth. So if we take a look at here, again, we should see 2 signals, right? And we see 2 signals, 2 hydrogen signals. And what we see here is that this one here, this signal is worth 3 hydrogens, and then this signal over here is worth 9 hydrogens. So it's a 1 to 3 ratio, but I will show you 3 hydrogens and 9 hydrogens. And we can see that with respect to the intensity, right? This signal right here is about 3 times more intense than the other signal. All right, so this is what we mean by integration. All right, so if we think about ethanol then, right? So here's a molecule ethanol. And let's say we make a little table here. We say, okay, number of signals, and then we also go with integration, right? How many signals are each of those worth? Well, hopefully we'll realize that there are 3 signals in ethanol, right? And we can see that here if I draw these out. All right, so these are HA, these are HB, and this is HC. So 3 signals here. So we'd say, okay, A, B, and C. And then if we looked at integration, well, again, integration is just telling us how many hydrogens are there of that kind. Well, we say, okay, well, there's 3 HAs, so good. So integration is 3. And then there's 2 HBs, so 2. And there's 1 HC. It is that simple, right? That's what integration is telling us. How many hydrogens of the same type are there? All right, so if we look at this molecule here, how many signals would you expect to see in this molecule? Go ahead, think about it. Yeah, in this molecule, you would expect to see 3 signals, right? You would expect to see 3 signals. We would see these hydrogens right here. That's 1 signal. Then we see these hydrogens here. That's another. And then these hydrogens here. That's another. So we see those 3 signals here. We're at that 4th step though. There are 3 signals, but all of the signals that we've discussed so far have been all single lines such as this, right? But that's only one kind of signal. That's what we call a singlet, right? That's what we call a singlet. But there are other types of signals. There's this one here. This is called a quartet. And there's this one right here. This is called a triplet, right? So still 3 signals, 1, 2, 3. Now they just look a little different. So what we're going to spend this portion of the video is discussing how do you determine what they're going to look like? So how they determine what they look like is going to be dependent on their neighbors. So their immediate neighbors, the atoms that are right next to them, are going to determine what each signal looks like. So for example, let's try this here. Let's just say hypothetical situation here. Let's say that I have this molecule here, and these two hydrogens are the same, so HA and HA, right? So in order to figure out what HA is going to look like, right, we have to look at its immediate neighbor. And we use the formula n plus 1, where n equals the number of neighboring hydrogens that are different. The number of neighboring hydrogens that are different. That's what n is, right? So if we look at this, okay, we say, okay, well, here's HA. It resides on this carbon right here. Let's see, I'm trying to. Well, it resides on this carbon over here. And so if we look at its immediate neighbor, which is this carbon right here, right? Well, how many hydrogens are there that are different from HA? None, right? They're both the same. So we would say 0 plus 1, this equals 1. This is going to look like a single line. And that single line is what we call a singlet, right? That single line is what we call a singlet. All right, so let's change it up a little bit. Again, hypothetical here. Let's say we have HA here. And now the neighboring hydrogen is different. Now let's say it's HB. Well, if we say that, then we say, okay, well then if we're trying to figure out what HA looks like, it's 0 plus, oh sorry, not 0, but rather it's 1 because n equals 1. 1 is the neighboring hydrogen that is different. So it's 1 plus 1, this equals 2. So in this case, we're going to see our two lines, same height here. This is what we call a doublet. All right, so we can continue on here. We can say, okay, now we're trying to figure out what this HA looks like. Let's say now there's two HBs right here, right? We're trying to figure out what HA looks like. Well, N, how many neighboring hydrogens that are different? There's 2. So 2 plus 1, that equals 3. And this is called a triplet, right? And we can keep going. If there were 3 neighboring hydrogens that were different, that'd be 3 plus 1, that equals 4. Right? It looks like a quartet. If there were 4 neighboring hydrogens that were different, it would be 4 plus 1, that equals 5. This is what we call a pentet. If there were 5 neighboring that were different, that's 5 plus 1, that is 6. That's a sextet. Remember, keep in mind that it's always symmetrical, right? It's always symmetrical. If we had 6, it's like a pyramid. That's a septet. And you can imagine as we keep going, we'd have an octet and a nonnet. And you might also notice that when we start getting close to here, they start to get very close to each other. And it might be hard to see. You might just see like a lot of mess and you can't really count it out. So if you ever hear multiplet, it also might be that they're so close to each other that we can't tell. So we might use the term multiplet. Now, the other thing that you want to keep in mind when we're thinking about these signals here is that, stop doing that. Give me my pencil. If I, there we go. Finally, again, y'all get to see me trying to work this out for you guys. Um, so the other thing that you want to keep in mind here, a little note here, hydrogens that are on oxygen or nitrogen do not get split, nor do they contribute to splitting. Right? They're not going to split like these did, and they're not going to contribute to splitting. Because if you remember, a hydrogen that's on a heteroatom, such as oxygen or nitrogen, it's an acidic proton, right? Which means that you can deprotonate it. You can take it off and put it back on. So the truth is when we dissolve these compounds in a solvent, this is constantly coming off and on, off and on. So because they're acidic, and because of their hydrogen bonding nature, they don't get split and they don't contribute to splitting because sometimes they're there, sometimes they're not there. Sometimes they're there, sometimes they're not there. So you just want to keep that in mind when we're doing these. And we'll do some examples of this also. All right, so here we go. So this is kind of the theory that I just went over. So if you want some examples here that might help to go through these slides. And I'm about to go through those slides here, a little bit more problem-based example here. So if we do this, then the question is, well, how many signals would you expect to see? So go ahead, think about this. How many signals would you expect to see in this molecule? Hopefully we see that there's going to be two signals, right? These would be HA right here, right? Those would be HA, and then this signal here would be HB. Right, so two signals. So if we made a little chart here, we would say, okay, signals A and B. Here's the integration. Right, so let's do integration here. So what would be the integration of A to B, do you think? Yeah, it should be 6 to 2, right? The integration, there's 6 HAs and 2 HBs. All right, and then now let's do splitting, right? Let's do splitting. So there's two ways that we can do the splitting here, and I'll show you both ways, and you determine which one works best for you. So here's our molecule. And we said that there were two different types of protons here. So we said that these were HA and these were HB, right? That's what we had mentioned here. So again, we're looking at the immediate neighbors here. We're looking at the immediate neighbors. So if we're looking at the immediate neighbors, this is one way that you can do it, all right? HAs live at this house right here. Let me use a highlighter, right? HA lives at this house. Here is the neighboring house. So you'll go to the immediate neighbor. Here's the neighboring house. The question is, how many hydrogens live at the neighboring house that are different from HA? That's the question. How many hydrogens live at the neighboring house that are different from HA? So if we look at it, we go 1 over. There's 2 there, so it would be 2 plus 1. That equals 3. That is going to be a triplet. Right? That's going to be a triplet. Right? So now let's look at HB. HB lives at the yellow house. Its immediate neighbors, right, to both sides here, its immediate neighbors are this pink house, right? So on one side, there's 3 hydrogens that live on that pink house. On the left side, there's another 3 hydrogens that live at that pink house. So that's a total of how many neighbors that are different from itself? A total of 6. So 6 plus 1, this equals 7. That's going to be a septet. Right? That's going to be a septet here. So this is how we determine this, right? You just go to its immediate neighbors and you count them and you add 1 and that tells you what the signals are. The other thing that you can do is you can count the number of sigma bonds. You can say once you go 3 sigma bonds, if you hit a hydrogen, then that counts as a neighbor. So here's an example. We're starting at this hydrogen right here, HA, and we're going to go 1, 2, 3. We hit a sigma bond. This one counts. Okay, we can go again. 1, 2, 3. Right, we hit a hydrogen. That counts. So there's only 2. So 2 plus 1 is 3. Personally, I like the houses, but work with whatever works for you. Okay, when determining the number of signals. All right. So that's what we see here. We see 2 signals, again, integration, and we see a septet and a triplet. The septet is worth 2 hydrogens, and the triplet is worth 6 hydrogens, right? So we see that here. All right, so let's try this one. How many signals would you expect to see on this molecule? Think about it. Good. Hopefully you say there are 3 signals and they're labeled here by the different colors. And if we think about the integration, what's the integration of the blue? 3. What's the integration of the red? 2. What's the integration of the green? 2. So this ratio would be 3, 2 to 2. All right, so now let's do some quizzes here. Let's start with this one. What would be the splitting of this blue hydrogen right here? What would be the splitting of this blue hydrogen signal? If you think it's a doublet, we're going to put A, triplet, B, C, quartet, D, sextet. Go ahead, click your answer. All right, hopefully you realize that for the blue hydrogen, it's going to be a triplet, right? These hydrogens live at this house. Here's the neighboring house. 2 hydrogens live there that are different from the blue ones, so 2 plus 1 is a triplet. All right. All right, so now let's do the red one, which are the ones in the center. So the ones in the center right here, these are the red ones. Go ahead. What type of signal would you expect to see? All right, so hopefully you realize it's a sextet, right? These hydrogens live at this house. Here's a neighboring house. There's 2 hydrogens that live here. Here's another neighboring house. 2 hydrogens that live there, a total of 5. 5 plus 1 is 6, so that's a sextet. What about this one here? Okay, so in this case, you would expect this to be a triplet also, right? These hydrogens live at this carbon. Here's the neighboring house. 2 live there, right? So 2 plus 1 is triplet. So when we look at this, that's exactly what we see here. We see 2 triplets and we see a sextet. The question is, which color is this triplet over here, right? What color is that one going to be? Is that going to be the green hydrogen, which is right here? Or is it going to be the blue hydrogen, which is over here? Which one is going to be the one that's at 3.7? Go ahead and click your answer. And hopefully we realize that that one's going to be the green hydrogen, right? Because it's next to the chlorine, right? And that chlorine has a de-shielding type of effect. So I hope that kind of clarifies and kind of really puts all of it together for you, right? Kind of brings it all together for you. Let's try some more here. How many signals would you expect to see in this molecule here? Hopefully you say there are going to be 3 signals. Very good. And we can think about that integration. That integration would be 3, 2 to 1. Okay. All right, so let's go ahead and click in again. What would be the signal of the blue hydrogen? Good. Hopefully you realize that this is a triplet, right? Let's keep going. The red hydrogen. Hopefully you realize that this is a pentet. Good. And the green hydrogen. All right. Hopefully you realize that that's a triplet. Good. All right. Now, so if we look at this again, that's what we see. Notice that this one, the previous one was around 3.7. This triplet now is much closer to 5.5. Why do you think that's the case? Yeah, in this case, we actually see that we have 2 chlorines, so that's going to have an even stronger de-shielding effect. All right, so let's finish off for ethanol here. So when we did ethanol, we said that we had 3 signals. Right, we said we had 3 signals here. So this is HA, HB, and HC. So we had a table here. We had number of signals. We said A, B, and C. And then we had integration. And we said that it was 3, 2, 1. And we can add a new one for splitting. And if we look at HA, we say, okay, well, these hydrogens live at this house. The neighboring house right here has 2 that are different from itself. So 2 plus 1, that is a triplet. Now, if we look at B, we say, okay, on this side over here, there's 3 HAs, so that's 3 there, and then there's 1 HC. However, remember what we said. Hydrogens that are on oxygen or nitrogen do not get split, nor do they contribute to splitting. So even though we see 1 to this side, we're not going to count it. Because remember, sometimes it's there, sometimes it's not, right? So if we actually look at B, it's only 3. So we say 3 plus 1, that's going to be a quartet. And if we look at C, remember, it doesn't get split, nor does it contribute to splitting. So we pretend sometimes it's there, sometimes it's not. So we're just going to say 0 plus 1, that is going to be a singlet, right? So that is, so if we look at the NMR, that's what we see here. We see a triplet, we see a singlet, and we see a quartet, right? So we see all 3 here. Now some of you might be wondering, says, wait, why is the singlet at 3? Shouldn't that be the one that's the most downfield? In fact, the quartet, which is this one right here, this is the quartet, HB, that's the most downfield. Why is it not HC? Remember, sometimes it's there, sometimes it's not. And if you look at your sheet that's on Blackboard, you'll notice that it's a really long range. And again, because sometimes it's there, sometimes it's not. All right. So this is NMR in a nutshell here. So you want to make sure that you're familiar with the NMR and how this functions, right? And how you can interpret this. The next video that we're going to talk about is IR, which goes hand in hand. You'll notice that that's going to be a lot shorter a video, just because IR is a little bit much more straightforward compared to NMR. So I encourage you to watch the videos on Panapto that's going to go over the assignment and how to complete the assignment and the worksheet. So you should find that in the same folder as you found this video. So I encourage you to watch that just to get the instructions. All right, so until next time, guys, I will see you.